Hello there, dear wanderer of the night. Thank you for finding your way here to this quiet corner of the cosmos. Tonight, we're going to peer into the darkest places in the universe, places where our most cherished laws of physics simply break. We'll explore what happens when the universe gets so extreme that even Einstein's brilliant theories throw up their hands in defeat. We'll visit the edges of black holes, where time stops making sense and reality itself becomes uncertain. Where are you listening from tonight? And what time is it in your world right now? If you find comfort in these gentle explorations of cosmic mysteries, please consider giving this a like or subscribing. It helps me continue creating these peaceful journeys through the strange and wonderful universe we call home. Now, a small warning: side effects of this journey may include existential vertigo, a sudden urge to question everything you thought you knew about reality, and possibly dreaming in curved space-time. You might also develop an inexplicable fondness for mathematical infinities and find yourself explaining relativity to your houseplants. So settle in, wherever you are. Let your breathing slow. Tonight, we're going to discover that the universe is far stranger than we ever imagined. And sometimes, the most beautiful thing about science is admitting when we're completely wonderfully lost. Let's begin. Close your eyes for a moment and imagine you're holding a soft, stretchy piece of fabric. Maybe it's an old bedsheet or a piece of silk. Now picture placing a heavy marble right in the center. Watch how the fabric dips and curves around that weight, creating a gentle, bowl-shaped depression. This simple image captures one of the most revolutionary ideas in all of science. For centuries, we thought of space as a rigid stage where the cosmic drama played out. Time was the steady drumbeat marking each moment. But Einstein showed us something far more beautiful and strange. Space and time aren't separate things at all. They're woven together into a single flexible fabric we call space-time. When you place that marble on the fabric, you're doing exactly what massive objects do to space-time. The sun creates a depression in the cosmic fabric, and Earth rolls around the edge of that depression like a ball circling a funnel. We call this rolling motion gravity, but it's really just the natural consequence of curved space-time. Think about walking across a perfectly flat field versus walking across rolling hills. On the flat field, you'd naturally walk in straight lines, but on the hills, the landscape itself guides your path. You might find yourself curving left around a hill or sliding down into a valley. Space-time works the same way. The fabric of space-time is incredibly smooth and gentle around small objects like Earth. The curve is so gradual that it takes us a year to complete one orbit. But as objects get more massive, the depression gets deeper and steeper. A star creates a deeper well than a planet. A dead star creates an even deeper one. And then there are black holes. These cosmic monsters create such extreme curves in space-time that they're like tears in the fabric itself. The gentle rolling hills become vertical cliffs. The smooth valleys become bottomless pits. And right at the edge of these pits, something extraordinary happens. Our understanding of physics begins to unravel. You see, all of our equations and theories work beautifully when space-time is gently curved. We can predict the orbits of planets, the behavior of satellites, even the bending of light around distant galaxies. But as we approach a black hole, the curvature becomes so extreme that our mathematical tools start giving us impossible answers. Wikisi, all of our equations and theories work beautifully when space-time is gently curved. We can predict the orbits of planets, the behavior of satellites, even the bending of light around distant galaxies. It's like trying to use a ruler to measure the curve of a circle. When the curve is gentle, the ruler works fine. But when the curve becomes too tight, the ruler can't bend enough to follow it. Our physics equations are like that ruler. They work perfectly in the gentle curves of normal space-time, but they can't handle the extreme curves near black holes. This is where our story really begins. Because black holes don't just bend space-time, they break it. They create conditions so extreme that even our most sophisticated theories stumble and fall. And in those moments of failure, we glimpse something profound about the nature of reality itself. The ancient Greeks believed that the universe was fundamentally rational and knowable. They thought that with enough cleverness and mathematics, we could understand everything. But black holes whisper a different truth. They suggest that the universe might be fundamentally stranger than we can imagine. They show us that reality has edges, places where our knowledge simply runs out. Tonight, we're going to explore those edges together. We're going to visit the places where physics breaks down, where our best theories fail, and where the universe reveals its deepest mysteries. It's a journey that will challenge everything you think you know about time, space, and the nature of existence itself. Picture yourself standing at the edge of a vast canyon, looking down into layers of rock that tell the story of millions of years. Now, imagine that canyon getting deeper and steeper as you watch. The gentle slopes become cliff faces. The distant bottom disappears into shadow. This is what happens to space-time as objects become more and more massive. Every object with mass creates what we call a gravitational well. Your coffee cup creates a tiny, almost imperceptible dimple in space-time. Earth creates a deeper well, one strong enough to keep you firmly planted on its surface, and the moon dancing around it. The sun creates a well so deep that it holds 8 planets in its embrace, including our own Earth in its year-long waltz around the solar furnace. Solar furnace. But stellar objects can become much more extreme. When a massive star dies, it doesn't just fade away quietly, it collapses under its own weight, creating a well so deep that nothing, not even light itself, can climb back out. This is where our gentle metaphor of marbles rolling on fabric begins to break down. Because what we're describing isn't just a deeper well, it's a well that goes infinitely deep. Imagine trying to throw a ball out of a canyon. If the canyon is shallow, you can easily toss the ball over the rim. If it's deeper, you need to throw harder. But what if the canyon walls are so steep and so high that no matter how hard you throw, the ball always falls back down? That's what happens with black holes. They create wells in space-time so deep that even light, traveling at the universe's speed limit, can't escape. The mathematics of this situation is both beautiful and disturbing. As you approach a black hole, the equations that describe space-time begin to curve more and more dramatically. It's like watching a graph that starts gently and then suddenly shoots up toward infinity. The curves become so extreme that they break our geometric intuition entirely. Think about trying to draw a map of the surface of a sphere on a flat piece of paper. Near the equator, everything looks fine, whole. But as you try to include the poles, the map becomes increasingly distorted. Lines that should be parallel start to converge. Distances become impossible to measure accurately. The flat paper simply can't capture the curved reality of the sphere. This is exactly what happens to our physics near black holes. Our equations are like that flat map, and space-time near a black hole is like the curved surface of a sphere. But unlike a sphere, which has a manageable amount of curvature, the space-time around a black hole curves so dramatically that our mathematical maps become completely useless. The gravitational well doesn't just affect the paths of objects moving through space, it affects time itself. As you descend deeper into the well, time begins to slow down relative to the outside universe. What feels like a few minutes to someone falling into the black hole might appear to take hours, days, or even years to someone watching from a safe distance. This isn't just a theoretical curiosity, it's a fundamental breakdown in our understanding of reality. Because if time passes differently for different observers, then the question, what is happening right now, becomes literally meaningless. There is no universal now near a black hole. There is only a collection of different, incompatible perspectives on the same events. The deeper you go into the gravitational well, the more extreme these effects become. Near the very edge of the black hole, time dilation becomes so severe that a single second experienced by someone falling in corresponds to millions of years passing in the outside universe. The well becomes so steep that space-time itself begins to look less like a curved surface and more like a waterfall, with information and matter flowing inexorably toward the center. And at the very bottom of this well, Our equations predict something that makes physicists deeply uncomfortable. They predict a point where the curvature of space-time becomes infinite, where the density of matter becomes infinite, where the very concept of space and time cease to have meaning. This point is called a singularity, and it represents the complete breakdown of our understanding of the universe. But here's the thing that keeps physicists awake at night. We don't know if these infinite values are real, or if they're just a sign that our theories are broken. It's like reaching the edge of an old map where the cartographer wrote "Here be dragons." We don't know if there are actually dragons beyond the edge, or if we simply haven't learned how to make better maps yet. There's something profoundly unsettling about the moment when a trusted tool stops working. Imagine you're building a house, and your level, that reliable instrument that's helped you create perfectly straight walls, suddenly starts giving you impossible readings. The bubble floats in the middle when you're clearly on a slope. The measurements don't add up. You begin to question not just the tool, but your entire understanding of what level even means. This is precisely what happens to physicists when they peer too closely at black holes. The mathematical tools that have served us so well for centuries, the equations that predict the orbits of planets, the behavior of light, the flow of time, begin to give us answers that make no sense. They tell us that time stops. They tell us that space curves infinitely. They tell us that the laws of physics themselves cease to apply. The approach toward a black hole is deceptively gradual at first. Far away, everything behaves exactly as our theories predict. Light bends slightly around the massive object, just as Einstein's equations suggest it should. Time runs a little slower, but not enough to notice without extremely precise instruments. The fabric of space-time is curved, but gently, like a shallow hill rather than a cliff. But as you get closer, the effects become more pronounced. The bending of light becomes more dramatic. Time dilation becomes more noticeable. The curvature of space-time becomes steeper and steeper. And then, at a certain distance from the black hole, something extraordinary happens. You cross an invisible boundary where the normal rules of physics begin to break down entirely. This boundary isn't marked by any physical barrier. There's no wall, no sign, no sudden change in the environment. It's simply the point where space-time becomes so warped that our equations start producing mathematical infinities. Infinities are physics' way of throwing up its hands and saying, "I don't know what happens here." Imagine you're trying to divide a pizza among your friends. If you have 4 friends, each gets a quarter. If you have 8 friends, each gets an eighth. But what if you have 0 friends? Suddenly, you're trying to divide by 0, and mathematics breaks down completely. The answer isn't a number at all. It's undefined, meaningless, impossible. Black holes create similar mathematical impossibilities. They force us to divide by 0 in the equations of general relativity. They create scenarios where the curvature of space-time becomes so extreme that our mathematical tools simply can't handle it. We get infinities where we should get finite answers. We get contradictions where we should get consistency. The most disturbing part is that this breakdown doesn't happen at some impossibly distant or theoretical location. It happens at a specific, calculable distance from any black hole. For a black hole with the mass of our Sun, this boundary sits about 3 kilometers from the center. For the supermassive black holes at the centers of galaxies, it might be millions of kilometers away. But in every case, there's a precise point where our physics stops working. This isn't just an academic problem. It's a crisis that strikes at the heart of how we understand reality itself. Science is built on the assumption that the universe is rational and comprehensible. We believe that with enough careful observation and clever mathematics, we can understand how everything works. But black holes suggest that there might be aspects of reality that are fundamentally beyond our ability to comprehend. The breakdown of physics near black holes reveals something profound about the nature of knowledge itself. For centuries, we've been building increasingly sophisticated theories to explain the universe around us. Each new discovery seemed to expand our understanding, to bring us closer to a complete picture of reality. But black holes show us that our knowledge has boundaries. They show us that there are places in the universe where our best theories simply fail. This failure isn't necessarily permanent. Throughout history, scientists have encountered phenomena that their theories couldn't explain, only to develop new and better theories that could handle the previously impossible cases. When Newton's laws failed to explain the orbit of Mercury, Einstein developed general relativity. When classical physics couldn't explain the behavior of atoms, quantum mechanics emerged. But black holes present a different kind of challenge. They don't just require new theories, they require us to fundamentally rethink what we mean by space, time, and physical law. They force us to confront the possibility that reality might be stranger than we can imagine, that there might be aspects of the universe that are genuinely unknowable. And yet, there's something beautiful about this confrontation with the limits of knowledge. Black holes remind us that the universe is not a solved puzzle, but an ongoing mystery. They humble our scientific confidence while simultaneously inspiring our curiosity. They show us that even in an age of advanced technology and sophisticated mathematics, there are still dragons at the edges of our maps. Imagine standing at the edge of a vast waterfall, watching the river flow peacefully toward the precipice. There's a point, subtle but absolute, where the water commits to its fall. Before that point, a leaf floating on the surface might still be carried back upstream by an eddy or a reverse current. But once it crosses that invisible line, no force in the world can prevent its plunge into the abyss below. Black holes have a similar boundary, but far more mysterious and profound. We call it the event horizon, a name that captures both its function and its strangeness. It's the boundary beyond which events cannot be observed from the outside universe. It's the point of no return, where even the fastest thing in the universe, light itself, cannot escape the gravitational pull. But unlike the waterfall's edge, which you can see and touch and measure, the event horizon is invisible. It's not made of matter or energy. It's simply a location in space-time where the curvature becomes so extreme that the geometry of the universe itself changes in a fundamental way. Inside this boundary, all paths lead toward the center of the black hole. Outside, escape is still possible. At the boundary itself, reality becomes ambiguous in ways that challenge our deepest assumptions about the nature of existence. The size of this boundary depends on the mass of the black hole. For a black hole with the mass of our Sun, the event horizon would be about 6 kilometers across, small enough to fit inside a city, yet containing the mass of a star. For the supermassive black holes that lurk at the centers of galaxies, the event horizon might be larger than the orbit of Neptune. But in every case, it represents the same thing, the point where our ability to know what's happening inside comes to an end. Here's where things get profoundly strange. The event horizon isn't just a barrier to escape, it's a barrier to information itself. According to our understanding of physics, no information can travel from inside the event horizon to the outside universe. This means that once something crosses this boundary, it becomes forever unknowable to the rest of the cosmos. It's as if it has been edited out of the story of the universe. This information barrier creates a paradox that strikes at the heart of physics. On one hand, general relativity tells us that nothing special happens at the event horizon. Someone falling through would experience it as just another point in space. There would be no wall, no barrier, no moment of dramatic transition. The journey would continue smoothly toward the center of the black hole. But from the perspective of quantum mechanics, the event horizon is deeply problematic. Quantum theory insists that information cannot be destroyed. Every particle, every quantum state, every bit of information that has ever existed must be preserved somewhere in the universe. The event horizon seems to violate this fundamental principle by creating a boundary beyond which information disappears forever. This isn't just a technical disagreement between theories. It's a conflict between two different ways of understanding reality itself. General relativity presents a picture of smooth, continuous space-time, where the laws of physics work the same way everywhere. Quantum mechanics describes a universe where information is sacred and indestructible, where every quantum event leaves an indelible mark on the fabric of reality. The event horizon forces us to choose between these two pictures. but neither choice is satisfactory. If we accept that information can be destroyed at the event horizon, we must abandon quantum mechanics, the theory that explains atoms, chemistry, and most of the technology we use every day. If we insist that information must be preserved, we must somehow modify general relativity, the theory that explains gravity, the expansion of the universe, and the behavior of black holes themselves. The mystery deepens when we consider that the event horizon isn't fixed in space. As matter falls into a black hole, the event horizon grows larger. As the black hole slowly evaporates through Hawking radiation, the event horizon shrinks. This dynamic boundary seems to hover between existence and non-existence, between the known and the unknowable. Perhaps most disturbing of all is the realization that the event horizon exists in a state of fundamental ambiguity. Its location and properties depend on who is observing it, and from where an observer falling into the black hole would experience the event horizon as a mathematical abstraction, a coordinate boundary with no physical reality. An observer watching from far away would see the event horizon as a concrete, impenetrable barrier where time stops and physics breaks down. This ambiguity isn't just a matter of perspective or measurement difficulty, it's a fundamental feature of reality near black holes. The event horizon exists and doesn't exist simultaneously, depending on your point of view. It's both permeable and impermeable, both significant and meaningless, both real and imaginary. We're left with the uncomfortable realization that one of the most important boundaries in the universe, the edge of a black hole, cannot be unambiguously defined. It's a boundary that exists only relative to the observer, a point of no return that may not actually be a point at all. Picture two friends, Alice and Bob, standing at the edge of a cosmic precipice. Alice decides to take a leap into the black hole, while Bob stays behind to watch. What happens next depends entirely on whose story you choose to believe. And remarkably, both stories are equally true, according to our best understanding of physics. From Bob's perspective, watching from a safe distance, Alice's journey becomes increasingly surreal. As she approaches the event horizon, she appears to slow down. Her movements become sluggish, like a movie played in slow motion. The light from her body becomes redder and dimmer as it struggles to escape the black hole's gravitational pull. Time itself seems to be stretching like taffy around her. As Alice gets closer to the event horizon, the slowing becomes more dramatic. What she experiences as seconds stretch into minutes from Bob's perspective, then hours, then days. Eventually, Bob watches as Alice appears to freeze completely at the event horizon, her image growing dimmer and redder until it fades from view entirely. From his perspective, Alice never actually enters the black hole. She becomes frozen in time, forever suspended at the boundary between the known and unknown. But Alice tells a completely different story. From her perspective, nothing unusual happens. As she crosses the event horizon, she doesn't slow down, she doesn't freeze, she doesn't experience any dramatic transition. The event horizon passes by her like an invisible milestone on a cosmic highway. She continues falling toward the center of the black hole, picking up speed as she goes. Time flows normally for her. Space behaves predictably. Physics works exactly as it should. The difference between these two experiences isn't a matter of measurement error or observational limitation. It's a fundamental feature of how reality works near black holes. Both Alice and Bob are experiencing the truth, their own personal truth about what happens at the event horizon. But these truths are mutually incompatible. This creates a paradox that physicists call the firewall problem, though it's really more like the multiple reality problem. If Alice's experience is real, if she smoothly passes through the event horizon and continues falling, then Bob's observations must somehow be wrong or incomplete. But if Bob's observations are accurate, if Alice really does freeze at the event horizon, then Alice's experience of smoothly passing through must be an illusion. The paradox deepens when we consider what happens to information. From Bob's perspective, any information that Alice carries with her never actually enters the black hole. It remains frozen at the event horizon, preserved in the increasingly red-shifted light that she emits. This seems to solve the information paradox. No information is lost, because it never actually crosses the boundary. But from Alice's perspective, she definitely carries her information across the event horizon and into the black hole. Her memories, her quantum states, her physical composition, all of it passes the point of no return and heads toward the center. If Alice is right, then information does disappear behind the event horizon, violating quantum mechanics. The problem becomes even more complex when we consider that both Alice and Bob are making valid observations according to general relativity. Neither perspective is privileged or incorrect. Bob's observations of time dilation and redshift are accurate measurements of how space-time curvature affects light and matter. Alice's experience of smooth passage through the event horizon is an equally valid description of free fall in curved space-time. This isn't like the optical illusion, where one person sees a vase and another sees two faces. In that case, we know there's a single underlying reality, a drawing that can be interpreted in different ways. But with black holes, there might not be a single underlying reality at all. There might be multiple equally valid descriptions of what happens, with no way to reconcile them. Some physicists have proposed that the resolution lies in quantum mechanics. They suggest that the quantum nature of space-time itself might create a firewall at the event horizon, a barrier of highly energetic particles that would destroy Alice before she could pass through. This would resolve the paradox by ensuring that Alice never actually crosses the event horizon from anyone's perspective. But the firewall solution creates its own problems. It would mean that the event horizon is not the smooth, invisible boundary that general relativity predicts, but a violent, destructive barrier. It would require us to abandon our understanding of how space-time behaves in strong gravitational fields. Other physicists have suggested that the resolution might lie in the holographic principle, the idea that all the information in a volume of space can be encoded on its boundary. According to this view, Alice's information is indeed preserved at the event horizon, but in a form that's scrambled and encoded in ways we don't yet understand. But every proposed solution to the paradox creates new problems. Each attempt to reconcile Alice's and Bob's experiences requires us to abandon some fundamental principle of physics. We're left with the disturbing possibility that reality itself might be fundamentally inconsistent, that the universe might contain genuine contradictions that cannot be resolved. There's a moment in every detective story when the investigator realizes that the clues don't add up. The witness testimonies contradict each other. The physical evidence points in different directions. The timeline doesn't make sense. But unlike fictional mysteries, the contradictions surrounding black holes can't be resolved by finding the missing clue or identifying the unreliable witness. They seem to be fundamental features of reality itself. The event horizon paradox represents something unprecedented in the history of physics. For the first time, we have a situation where our two most successful theories, general relativity and quantum mechanics, don't just disagree about details. They give completely contradictory answers to the same question. It's as if we asked two master mathematicians to solve the same equation and got answers that were not just different, but mutually exclusive. General relativity insists that the event horizon is a smooth, invisible boundary where nothing dramatic happens. A falling observer would pass through it without noticing, continuing their journey toward the center of the black hole. Space and time remain well-behaved and predictable. The laws of physics continue to work normally. From this perspective, the event horizon is simply a coordinate boundary, like the equator on Earth, significant for navigation, but not physically special. But quantum mechanics tells a different story entirely. It demands that information cannot be destroyed, which means that anything falling into a black hole must somehow leave a trace that can be recovered. This requirement seems to conflict with the smooth passage through the event horizon. If information is preserved, then either the event horizon must be a barrier that prevents information from entering the black hole, or the information must somehow be copied, existing both inside and outside the event horizon simultaneously. The copying solution creates its own problems. Quantum mechanics also insists that information cannot be cloned, a principle called the no-cloning theorem. If Alice's information exists both inside and outside the event horizon, then we've violated this fundamental quantum principle. We're forced to choose between the no-cloning theorem and the preservation of information, but both are considered sacred in quantum mechanics. This crisis runs deeper than just theoretical physics. It challenges our basic assumptions about the nature of reality itself. Science is built on the belief that the universe is fundamentally rational and consistent. We assume that there's a single, objective reality that can be described by our theories, even if those theories are incomplete or approximate. But black holes seem to suggest that reality might be fundamentally ambiguous. They create situations where equally valid observations lead to contradictory conclusions. They force us to confront the possibility that the universe might not have a single consistent description. Different observers might live in different realities, with no way to reconcile their experiences. The philosophical implications are staggering. If reality is observer-dependent near black holes, what does that mean for our understanding of truth itself? How can we do science if there's no objective reality to study? How can we trust our theories if they give different answers to the same question? Some physicists have tried to resolve these contradictions by proposing new theories that modify either general relativity or quantum mechanics. String theory, loop quantum gravity, and other approaches attempt to create a unified description of space-time that avoids the contradictions. But these theories are still speculative and unproven. They might solve the black hole paradoxes, or they might create new ones. Other physicists have suggested that the contradictions might be fundamental features of reality that we need to accept rather than resolve. They propose that the universe might be genuinely inconsistent, that truth might be contextual rather than absolute. This view is deeply unsettling to many scientists, who see consistency as the bedrock of rational thought. The crisis extends beyond black holes themselves. If our theories break down in these extreme environments, what does that say about their validity in less extreme situations? If general relativity and quantum mechanics are both wrong about black holes, how can we trust them to describe atoms and galaxies? Perhaps most disturbing is the realization that this crisis might be permanent. Unlike previous conflicts between theories, which were resolved by discovering new physics, the black hole paradoxes might represent genuine limits to human knowledge. They might be pointing to aspects of reality that are fundamentally beyond our ability to understand or describe. The event horizon paradox has been with us for decades now, and despite the efforts of brilliant physicists around the world, no satisfactory resolution has emerged. Each proposed solution creates new problems. Each attempt to reconcile the contradictions requires us to abandon cherished principles of physics. We're left in a state of cosmic humility, forced to admit that there are aspects of the universe that we simply don't understand. Black holes have become mirrors, reflecting back our own limitations and assumptions. They remind us that the universe is under no obligation to make sense to us, that reality might be stranger and more complex than we can imagine. In the end, the event horizon paradox might be teaching us something profound about the nature of knowledge itself. It might be showing us that the universe is not a puzzle to be solved, but a mystery to be explored, a mystery that might never be fully understood, but which continues to inspire and humble us with its depth and complexity. Time, we like to think, is the universe's great constant. It ticks forward at a steady pace, hours marking our days and years with clockwork precision. We build our lives around this assumption, scheduling meetings, planning futures, marking anniversaries. But near black holes, time reveals itself to be far more malleable than we ever imagined. It stretches and warps like warm honey, flowing at different rates for different observers in ways that seem to mock our everyday experience. The first hint that time isn't as reliable as we thought came from Einstein's realization that time and space are intimately connected. Just as a massive object can bend the fabric of space, creating valleys and hills in the cosmic landscape, it can also bend the flow of time itself. The stronger the gravitational field, the more dramatically time is affected. Imagine you're watching a friend walk through a valley while you stand on a hilltop. If the valley is shallow, you might notice that your friend seems to be moving slightly slower than you'd expect. But if the valley is deep, carved by some cosmic force into a profound depression, your friend might appear to be moving in slow motion, their every gesture elongated and dreamlike. This is precisely what happens with time near massive objects. As you descend deeper into a gravitational well, time begins to slow down relative to observers at higher elevations. On Earth, this effect is tiny. A clock at sea level runs about 30 nanoseconds per year, slower than an identical clock on a mountaintop. You'd need atomic precision to detect such a difference. But near a black hole, time dilation becomes dramatic and unmistakable. The gravitational field is so intense that it creates profound distortions in the flow of time itself. What feels like normal time to someone falling into the black hole appears drastically slowed to an outside observer. It's as if the black hole is surrounded by invisible zones where time flows at different rates. The mathematics of this effect is both beautiful and disturbing. As you approach the event horizon of a black hole, time dilation approaches infinity. This means that events that take a finite amount of time for someone falling in would appear to take an infinite amount of time to an outside observer. Time doesn't just slow down, it approaches a complete stop. Think about trying to pour honey on a cold morning. At room temperature, honey flows smoothly and predictably, but as it gets colder, the flow becomes sluggish. The honey might drip so slowly that you barely notice it moving. Near a black hole, time behaves similarly. The intense gravitational field makes time flow so slowly that it becomes almost motionless. This isn't just a theoretical curiosity. GPS satellites orbiting Earth experience measurable time dilation due to both their speed and their position in Earth's gravitational field. Without correcting for these relativistic effects, GPS would be off by several miles within a single day. The satellite's clocks literally run faster than clocks on Earth's surface because they're further from Earth's gravitational center. Near a black hole, these effects become extreme beyond imagination. If you were falling toward the event horizon, while a friend watched from a safe distance, they would see your movements become increasingly sluggish. Your gestures would slow to a crawl. Your speech would deepen and stretch until it became an incomprehensible drone. Eventually, you would appear to freeze completely, your image growing dimmer and redder as the light from your body struggled to escape the black hole's gravitational pull. But here's the truly mind-bending part. From your perspective, falling toward the black hole, nothing unusual would happen to time at all. Your watch would tick normally. Your thoughts would flow at their usual pace. You would experience time exactly as you always have. The dramatic time dilation would be completely invisible to you. This creates a profound asymmetry in the universe. Time dilation is not mutual near black holes. While you experience normal time flow, observers at different distances from the black hole experience time at different rates. There's no universal clock, no cosmic timekeeper marking moments for everyone. Time becomes personal, subjective, dependent on your location in the gravitational field. The implications are staggering. If time flows differently in different regions of space, then the question, what is happening right now, becomes meaningless. There is no universal now near a black hole. Events that are simultaneous for one observer might be separated by hours, days, or even years for another observer. This breakdown of simultaneity strikes at the heart of our understanding of causality. If time flows differently for different observers, then the order of events becomes ambiguous. Something that happens before something else for one observer might happen after it for another observer. The universe near black holes becomes a place where cause and effect become tangled in ways that challenge our basic assumptions about reality. Time dilation near black holes also creates practical paradoxes. If you could somehow hover just outside the event horizon and then return to Earth, you would find that far more time had passed on Earth than you experienced. Inirrevered mornisi gervireviendev. You could potentially travel to the future by spending time in the intense gravitational field of a black hole, but you could never return to the past. There's something deeply unsettling about watching someone you care about freeze in time. Not the playful freeze of a childhood game, but a cosmic freezing that stretches a single moment into eternity. This is exactly what happens when you watch someone fall into a black hole. They become trapped in a moment that never ends, suspended forever at the edge of the unknowable. From your safe vantage point, far from the black hole, you watch your friend approach the event horizon with growing concern. At first, their journey looks normal, if somewhat dramatic. They're falling freely through space, accelerating under the black hole's gravitational pull. Their radio messages reach you clearly, describing their experience in real time. Everything seems predictable, even if the outcome is tragic. But as your friend gets closer to the event horizon, something strange begins to happen to their image. They start to slow down, as if they're moving through increasingly thick syrup. Their movements become sluggish, their gestures stretched out in time. When they wave to you, their hand seems to take forever to complete its arc through space. The slowing becomes more pronounced as they approach the event horizon. What they experience as normal motion, perhaps a few seconds of falling, appears to you to take minutes, then hours, then days. Their voice, transmitted by radio, becomes deeper and more stretched out as the time dilation effect grows stronger. Eventually, their words become so elongated that they're incomprehensible, like a recording played at impossibly slow speed. As your friend reaches the event horizon, the slowing becomes infinite. From your perspective, they appear to stop completely, frozen at the boundary between the known and unknown universe. Their image hangs there, motionless, like a photograph suspended in space. Time itself seems to have stopped for them, trapping them in a single moment that will last forever. But there's more to this cosmic freezing than just the appearance of stopped time. The light from your friend's body becomes increasingly redshifted as it struggles to escape the black hole's gravitational field. Just as the sound of a retreating siren becomes lower in pitch, the light from your friend becomes redder and dimmer. Their image doesn't just freeze, it slowly fades away, becoming redder and weaker until it disappears entirely. This fading happens because light loses energy as it climbs out of the black hole's gravitational well. The photons from your friend's body have to work harder and harder to reach you as they get closer to the event horizon. Eventually, they become so redshifted that they fall outside the visible spectrum entirely. Your friend's image doesn't just freeze, it slowly disappears into the infrared, and then into radio waves, and finally into nothing. The mathematics of this process is both precise and disturbing. The time dilation factor approaches infinity as your friend approaches the event horizon. This means that finite amounts of time for them correspond to infinite amounts of time for you. From your perspective, your friend never actually crosses the event horizon. They remain forever frozen at the boundary, their image growing dimmer and redder, but never quite disappearing. This creates a profound paradox. If your friend never crosses the event horizon from your perspective, then where do they go? How can they simultaneously fall into the black hole and remain forever suspended at its edge? The answer depends entirely on whose perspective you adopt, and this dependence reveals something deeply troubling about the nature of reality itself. The frozen moment at the event horizon also creates problems for our understanding of black hole physics. If matter never actually crosses the event horizon from the perspective of outside observers, then how do black holes grow? How do they consume matter and energy? The mathematics suggests that black holes should remain forever on the verge of swallowing matter without ever actually doing so. Some physicists have suggested that the frozen image at the event horizon contains all the information about everything that has ever fallen into the black hole. From this perspective, the event horizon acts like a cosmic hard drive, storing compressed information about every particle, every atom, every bit of matter that has approached the black hole. The information is preserved in the frozen light at the boundary, scrambled and encoded in ways we don't yet understand. But this information storage creates its own mysteries. If the information is preserved at the event horizon, then it should be recoverable in principle. But how can we decode information that's been redshifted into oblivion? How can we read a cosmic hard drive that's written in light so faint it's effectively invisible? The frozen moment also raises questions about the nature of time itself. If your friend is truly frozen at the event horizon from your perspective, then they exist in a state outside of time. They become a permanent feature of the universe, neither moving forward nor backward in time, but suspended in an eternal present. This timeless existence challenges our basic assumptions about the nature of consciousness and experience. Perhaps most disturbing is the realization that this frozen moment is not just a theoretical curiosity. Every piece of matter that has ever approached a black hole, every star, every planet, every spacecraft, remains frozen at the event horizon. From the perspective of the outside universe, black holes are surrounded by an invisible graveyard of frozen images, a cosmic museum of everything that has ever dared to venture too close. The word now seems so simple, so fundamental to our understanding of existence. Right now, you're reading these words. Right now, somewhere else, a star is being born. Right now, in another part of the universe, a planet is orbiting its sun. We use now to create a sense of universal simultaneity, a shared moment that connects all of existence. But near black holes, this simple word becomes meaningless in ways that challenge everything we think we know about the nature of time and reality. Let's return to our thought experiment with two friends, Alice falling into a black hole and Bob watching from a safe distance. When Bob checks his watch and says, "It's now 3 p.m., what time is it for Alice?" The question seems straightforward, but it reveals one of the most profound mysteries of modern physics. From Bob's perspective, Alice's time has slowed down dramatically. When his watch shows that an hour has passed, Alice's watch might show that only a few minutes have elapsed. But from Alice's perspective, her time is flowing normally. She experiences each minute as a full minute, each hour as a full hour. Her watch ticks at exactly the same rate it always has. The problem is that there's no universal clock to settle the dispute. There's no cosmic timekeeper marking moments for everyone in the universe. Time near black holes is personal, subjective, dependent on your location and motion. Bob's now and Alice's now are completely different concepts, and there's no way to reconcile them. This relativity of simultaneity becomes even more complex when we consider multiple observers at different distances from the black hole. Imagine three friends, Alice falling in, Bob watching from a distant safe point, and Charlie hovering at an intermediate distance. When Bob's watch shows 3 p.m., Alice's watch might show 2:30 p.m., and Charlie's watch might show 2:45 p.m. Each observer experiences time at a different rate, and each has their own valid definition of now. The situation becomes even more bizarre when we consider events happening at different locations. Suppose Alice drops a red ball when her watch shows 2:30 p.m. and Bob simultaneously fires a blue laser when his watch shows 3 p.m. Which event happened first? The answer depends entirely on who you ask. From Bob's perspective, the events were simultaneous. From Alice's perspective, she dropped the ball before Bob fired the laser. From Charlie's perspective, Bob fired the laser before Alice dropped the ball. This isn't just a matter of measurement error or communication delay. It's a fundamental feature of how time works in curved space-time. The order of events becomes ambiguous, dependent on the observer's location in the gravitational field. There's no absolute sequence of events, no universal timeline that everyone can agree upon. The breakdown of simultaneity has profound implications for our understanding of causality. If the order of events is ambiguous, then the relationship between cause and effect becomes unclear. Something that appears to be a cause from one perspective might appear to be an effect from another perspective. The universe near black holes becomes a place where cause and effect become tangled in ways that defy our everyday understanding. This relativity of time also creates practical communication problems. If Alice tries to send a message to Bob, when will he receive it? The answer depends not just on the speed of light, but on the complex interplay between time dilation and the curved space-time around the black hole. Messages sent at regular intervals from Alice's perspective might arrive at Bob's location at increasingly long intervals. Eventually, the communication would become so stretched out in time that it would be effectively impossible. The psychological implications are equally disturbing. If Alice and Bob can't agree on when events happen, then they can't share a common experience of reality. They become isolated in their own time streams, each living in a personal version of the universe that can't be reconciled with anyone else's experience. The shared reality that we take for granted in everyday life becomes impossible near black holes. Some physicists have tried to resolve these problems by proposing alternative definitions of simultaneity for observers in curved spacetime. But every proposed solution creates new problems. Some definitions work for certain observers, but not others. Some preserve causality, but violate other principles of physics. Some maintain consistency, but require us to abandon our intuitive understanding of time. The relativity of now near black holes also affects our understanding of the universe's history. If different observers experience time at different rates, then the age of the universe becomes ambiguous. Some observers might measure the universe to be older than others, depending on their location and motion. The cosmic timeline becomes personal rather than universal. Perhaps most unsettling is the realization that this relativity of time is not just a theoretical curiosity. It's a fundamental feature of the universe we live in. Even on Earth, clocks at different elevations run at slightly different rates due to gravitational time dilation. GPS satellites must account for this effect to maintain accuracy. The relativity of now is all around us, subtle but real. Near black holes, these effects become extreme and undeniable. They force us to abandon our intuitive understanding of time as a universal constant. They show us that the universe is far stranger than we ever imagined, where time itself becomes a personal, subjective experience rather than a shared foundation of reality. Deep within the heart of quantum mechanics lies a principle so fundamental that physicists consider it sacred. Information cannot be destroyed. This might sound abstract, even philosophical, but it's actually one of the most concrete and testable ideas in all of physics. Every particle, every quantum state, every interaction in the universe leaves an indelible mark on reality. Nothing is ever truly forgotten. Nothing is ever completely erased. The universe, in this view, is like a cosmic library where every book that has ever been written is preserved forever, even if we can't always find the right shelf. This principle of information conservation isn't just a nice idea, it's the foundation upon which our entire understanding of quantum mechanics rests. When a photon is absorbed by an atom, the information about that photon's energy, momentum, and polarization is preserved in the excited state of the atom. When a particle decays, the information about the original particle is preserved in the properties of the decay products. When quantum states evolve, they do so in ways that preserve every bit of information about their initial conditions. The preservation of information is what makes quantum mechanics reversible, at least in principle. If you know the exact quantum state of a system at any moment, you can, in theory, calculate what its state was at any earlier time. The equations of quantum mechanics work equally well running forward or backward in time. The universe has a perfect memory, recording every quantum event in the correlations and entanglements between particles. This principle has been tested countless times in laboratories around the world. When physicists collide particles in accelerators, they can account for every bit of energy and momentum, every quantum number and symmetry. When they study the decay of radioactive nuclei, they find that the information about the original nucleus is perfectly preserved in the decay products. When they manipulate quantum systems in quantum computers, they find that information can be scrambled and spread out, but never destroyed. The conservation of information is so fundamental that it's built into the very structure of quantum field theory. The mathematical framework that describes particle physics requires that information be preserved in every interaction. Violating this principle would be like discovering that mathematics itself is inconsistent. But black holes seem to violate this sacred principle in the most dramatic way possible. When matter falls into a black hole, it appears to carry its information past the event horizon and into the unknowable interior. From the perspective of the outside universe, this information becomes inaccessible, locked away behind the event horizon where no signal can escape. The information doesn't just become difficult to retrieve, it becomes fundamentally unknowable. The problem becomes even more acute when we consider what happens to black holes over cosmic time. Stephen Hawking showed that black holes actually evaporate, slowly radiating away their mass and energy through a process now known as Hawking radiation. This radiation is thermal, random, carrying no information about what fell into the black hole. It's like the difference between a meaningful message and random static. Imagine throwing a library into a furnace. The books burn, releasing heat and light and ash. But the heat and light carry no information about the words that were on the pages. The knowledge contained in the books is destroyed forever. This is what seems to happen when matter falls into a black hole, and the black hole subsequently evaporates. The information is converted into thermal radiation that carries no memory of its origin. The implications are staggering. If information can be destroyed in black holes, then the entire framework of quantum mechanics is wrong. The equations that describe atoms and molecules, the principles that govern chemistry and biology, the foundations of quantum computing, all of it would be built on false assumptions. The universe would not be a perfect recording system, but a forgetful one, where the past can be erased and the future becomes fundamentally unpredictable. Some physicists have suggested that the information is not actually destroyed, but somehow encoded in the Hawking radiation in ways we don't understand. They propose that the thermal radiation only appears random because we don't know how to decode it. The information is preserved, but scrambled in incredibly complex ways that make it practically impossible to retrieve. But this solution creates its own problems. If the information is encoded in the Hawking radiation, then the radiation can't be truly thermal. It must carry subtle correlations and patterns that encode the information about everything that ever fell into the black hole. These correlations would be incredibly complex, potentially more complex than anything we can imagine or measure. The information paradox also raises questions about the nature of information itself. What exactly is information in the context of quantum mechanics? Is it a fundamental property of reality, like energy or momentum, or is it an emergent concept that only makes sense in certain contexts? The debate over black hole information has forced physicists to confront these deep questions about the nature of reality itself. The stakes couldn't be higher. If information can be destroyed in black holes, then we need to fundamentally rethink our understanding of quantum mechanics. If information is preserved, then we need to explain how it escapes from behind the event horizon. Either way, black holes are forcing us to confront the limits of our understanding and to question some of our most basic assumptions about the nature of reality. Black holes, those cosmic monsters that devour everything in their path, have a secret. They're dying. Not quickly, not dramatically, but slowly and inevitably, like ancient stars burning out in the depths of space. This death is so gradual that it makes the aging of mountains seem rapid by comparison. Yet it's happening. And when it does, it threatens to take all the information that ever fell into the black hole with it into oblivion. The story of black hole death begins with one of the most beautiful and counterintuitive discoveries in theoretical physics. In the 1970s, Stephen Hawking realized that black holes aren't completely black. They actually emit radiation, glowing faintly like dying embers in the cosmic dark. This radiation doesn't come from inside the black hole. Nothing can escape from there. Instead, it emerges from the quantum foam of empty space just outside the event horizon. Quantum mechanics tells us that empty space isn't really empty. It's filled with virtual particles, fleeting pairs of matter and antimatter that pop into existence and then annihilate each other in tiny fractions of a second. These quantum fluctuations happen everywhere in the universe, but they're usually too brief and too small to notice. Near black holes, however, something remarkable happens to these virtual particles. When a particle-antiparticle pair appears near the event horizon, the intense gravitational field can tear them apart before they have a chance to annihilate. One particle falls into the black hole while the other escapes to infinity. The escaping particle becomes real, carrying away a tiny amount of energy. The black hole, having lost this energy, becomes slightly less massive. This is Hawking radiation, the slow leak of energy that causes black holes to evaporate. The process is extraordinarily slow, A black hole with the mass of our Sun would take longer than 10 circumflex 67 years to evaporate completely, a time span so vast that it dwarfs the current age of the universe by a factor of trillions upon trillions. During this time, the black hole would emit radiation at a temperature of about 60 billionths of a degree above absolute zero, making it far colder than the cosmic microwave background that fills the universe. But smaller black holes evaporate faster. The relationship between mass and evaporation time is inverse. The smaller the black hole, the faster it dies. A black hole with the mass of a mountain would evaporate in less than a second, releasing the energy equivalent of millions of hydrogen bombs. A black hole with the mass of a car would evaporate in about 10 circumflex 21 seconds, faster than light can travel across a proton. As a black hole evaporates, it grows hotter and brighter. The temperature of Hawking radiation is inversely proportional to the black hole's mass. So as the black hole gets smaller, its temperature increases. In its final moments, a black hole becomes incredibly hot and bright, releasing its remaining energy in a brilliant flash before disappearing completely. This evaporation process seems to create a catastrophic problem for the conservation of information. When matter falls into a black hole, it carries information with it, information about its quantum state, its history, its interactions with other particles. This information appears to be trapped behind the event horizon, inaccessible to the outside universe. But when the black hole evaporates, where does this information go? The Hawking radiation appears to be completely thermal, random, structureless, carrying no information about what fell into the black hole. It's like the difference between a meaningful book and a pile of randomly arranged letters. The book contains information. The random letters contain none. If the Hawking radiation is truly thermal, then all the information that ever fell into the black hole is destroyed when the black hole evaporates. This creates what physicists call the information paradox. On one hand, quantum mechanics insists that information cannot be destroyed. On the other hand, general relativity seems to allow black holes to destroy information through evaporation. Both theories can't be right, but both have been tested extensively and found to be accurate in their respective domains. The paradox becomes even more troubling when we consider the implications for the universe as a whole. If information can be destroyed in black holes, then the entire history of the universe could potentially be erased. Every star that has ever formed, every planet that has ever existed, every life form that has ever evolved, all of it could be reduced to thermal radiation that carries no memory of its origin. Some physicists have proposed that the information is somehow encoded in the Hawking radiation, but in ways so subtle and complex that we can't detect it. They suggest that the radiation only appears thermal because we don't know how to decode the information it carries. The information is preserved, but scrambled in ways that make it practically impossible to retrieve. But this solution raises its own questions. If the information is encoded in the Hawking radiation, then the radiation can't be truly random. It must carry subtle correlations that encode the information about everything that ever fell into the black hole. These correlations would be incredibly delicate, requiring measurements of impossible precision to detect. The information paradox remains one of the most profound unsolved problems in physics. It strikes at the heart of our understanding of reality itself, forcing us to question whether our most successful theories are fundamentally correct or merely approximations that break down in extreme conditions. The information paradox remains one of the most profound unsolved problems in physics. Sometimes the most profound crises in science come not from what we discover, but from what we realize we cannot reconcile. The information paradox represents exactly this kind of crisis, a moment when two of our most successful theories look each other in the eye and declare that they cannot both be true. It's as if we discovered that our most trusted maps of reality are actually maps of different worlds entirely. Quantum mechanics stands as one of the greatest intellectual achievements in human history. It explains the behavior of atoms and molecules, the nature of chemical bonds, the workings of semiconductors and lasers. It has given us computers, medical imaging, GPS satellites, and countless other technologies that define modern life. More importantly, It has never failed a single experimental test. Every prediction it makes, no matter how counterintuitive, has been confirmed by observation. At the heart of quantum mechanics lies the principle of unitarity, the idea that quantum evolution is reversible and information-preserving. This principle isn't just a nice mathematical property, it's fundamental to the consistency of the theory. Without unitarity, quantum mechanics would predict that probabilities don't add up to 1, that energy isn't conserved, that the universe would gradually decay into inconsistency. Unitarity means that if you know the complete quantum state of a system at any moment, you can calculate what its state was at any earlier time, or what it will be at any future time. The evolution of quantum systems is like a movie that can be played forward or backward. Every frame contains enough information to reconstruct all the other frames. Information is never lost, only transformed. This principle has been tested in countless experiments. When particles interact, scatter, or decay, every bit of information about their initial states is preserved in the final states. The information might be scrambled, spread out, or encoded in complex correlations, but it's never destroyed. Even in the most chaotic quantum systems, information remains conserved. But black holes seem to violate this sacred principle. When matter falls past the event horizon, it appears to carry its quantum information into a region where it can never be retrieved. The information becomes causally disconnected from the rest of the universe. It's not just hidden or hard to access. It's fundamentally unknowable. The violation becomes even more dramatic when we consider Hawking evaporation. As a black hole slowly radiates away its mass, it eventually disappears completely. If the Hawking radiation is truly thermal, random and structureless, then all the quantum information that ever fell into the black hole is destroyed when the black hole evaporates. The information doesn't just become inaccessible, it ceases to exist entirely. This creates an impossible choice for physicists. Either quantum mechanics is wrong, in which case we need to abandon the theory that explains most of modern physics, or general relativity is wrong, in which case we need to abandon our best theory of gravity and space-time. Neither option is acceptable, yet one of them must be true. Some physicists have tried to resolve the paradox by modifying quantum mechanics. They propose that information can be destroyed in black holes, but only in ways that preserve the essential consistency of quantum theory. These modifications are subtle and carefully crafted to avoid contradicting any known experimental results. But modifying quantum mechanics is like trying to remove a single thread from a tapestry without causing the entire structure to unravel. Quantum mechanics is so tightly woven that changing any part of it threatens to destroy the whole theory. The principle of unitarity isn't just a nice feature of quantum mechanics, it's essential to its mathematical consistency. Other physicists have tried to resolve the paradox by modifying general relativity. They propose that black holes don't actually destroy information, but instead preserve it in ways that we don't yet understand. Maybe the information is encoded in the curvature of space-time itself, or in the quantum geometry of the event horizon. But these solutions create their own problems. If information is preserved in black holes, then the event horizon cannot be the smooth, invisible boundary that general relativity predicts. The preservation of information seems to require a firewall at the event horizon, a barrier of high-energy particles that would destroy anything trying to cross it. This firewall would violate the principle of general relativity that says nothing special happens at the event horizon. The information paradox has been with us for decades, and despite the efforts of brilliant physicists around the world, no satisfactory resolution has emerged. Every proposed solution creates new problems. Every attempt to preserve one principle seems to violate another. We're left with the disturbing possibility that our understanding of reality is fundamentally flawed. Perhaps most troubling is the realization that this paradox strikes at the heart of the scientific method itself. Science is built on the assumption that nature is consistent and rational. We believe that there's a single objective reality that can be described by our theories. Fearful, troubling, is the realization that this paradox strikes at the heart of the scientific method itself. But the information paradox suggests that this assumption might be wrong, It suggests that the universe might be fundamentally inconsistent, that there might be aspects of reality that cannot be reconciled with our rational understanding. The quantum mechanical crisis posed by black holes is more than just a technical problem for physicists. It's a profound challenge to our understanding of the nature of reality itself. It forces us to confront the possibility that the universe is stranger and more complex than we can imagine, and that our most cherished beliefs about the nature of knowledge and reality might be nothing more than comfortable illusions. There's a peculiar moment in mathematics when the numbers stop making sense. It happens when you try to divide by zero, when you attempt to find the square root of a negative number, when you push an equation beyond its natural limits. The calculator displays error, the computer program crashes. The mathematical universe itself seems to shrug and say, "I don't know what you're asking me." At the center of every black hole, our equations encounter exactly this kind of mathematical breakdown. But instead of a simple error message, we get something far more disturbing. A prediction of infinite density, infinite curvature, and the complete collapse of space-time itself. This mathematical catastrophe has a name: the singularity. It's the point where all the matter that has ever fallen into the black hole is compressed into a region of literally zero volume. Not very small. Zero. Not nearly zero. Exactly zero. The density at this point becomes infinite. The gravitational field becomes infinite. The curvature of space-time becomes infinite. And whenever physics encounters infinity, it's usually a sign that something has gone terribly wrong with our understanding. The mathematics that leads to this conclusion is both elegant and terrifying. Einstein's equations of general relativity describe how matter and energy curve space-time, and how this curved space-time affects the motion of matter and energy. For most situations, these equations work beautifully. They predict the orbits of planets, the bending of light around massive objects, the expansion of the universe itself. But when you apply them to the interior of a black hole, they lead inexorably to this point of infinite density and curvature. Imagine trying to fit all the water in the ocean into a space smaller than a grain of sand, then smaller than an atom, then smaller than a proton, and keep going until you reach zero volume. The mathematics of black holes suggests that this is exactly what happens to all the matter that falls past the event horizon. It gets compressed into a point of infinite density, a mathematical object that has mass but no volume, energy but no extent. The singularity isn't just a point in space, it's a point where space itself breaks down. At the singularity, the very concepts of distance, time, and geometry lose their meaning. The curvature of space-time becomes so extreme that space and time become infinitely warped. It's like trying to draw a map of the Earth's surface that includes the point at infinity. The mathematics simply cannot handle such extreme conditions. This mathematical breakdown is deeply unsettling to physicists. Science is built on the assumption that the universe is rational and describable through mathematics. We believe that every phenomenon, no matter how strange or complex, can ultimately be understood through careful observation and mathematical analysis. But the singularity suggests that there are aspects of reality that might be fundamentally beyond mathematical description. The problem is compounded by the fact that the singularity is not just a mathematical curiosity, it's a prediction that general relativity makes about the real physical universe. According to our best theory of gravity, every black hole contains a singularity at its center. These infinities aren't just mathematical artifacts, they're supposed to be actual features of space-time. But infinity is not a number. It's a concept that represents the absence of limits, the breakdown of measurement, the point where mathematics stops making sense. When a physical theory predicts infinity, it's usually a sign that the theory has been pushed beyond its domain of validity. It's like using a thermometer to measure the temperature of a volcano. The instrument breaks down before it can give you a meaningful answer. The singularity problem is made even more troubling by the fact that it appears to be unavoidable. Once matter crosses the event horizon of a black hole, general relativity predicts that it must eventually reach the singularity. There's no force in the universe that can stop this collapse. No material, no matter how strong, can resist the infinite curvature of space-time near the singularity. Intris and Darius 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 and Darius. This prediction creates a paradox for our understanding of physics. On one hand, general relativity is one of our most successful theories, confirmed by countless experiments and observations. On the other hand, it predicts the existence of singularities, regions where the theory itself breaks down. It's as if our most trusted map of reality includes regions labeled "Here be dragons," where the map itself admits it doesn't know what exists. Some physicists have suggested that the singularity is not a real physical object, but rather a sign that general relativity is incomplete. They argue that when space-time curvature becomes extreme enough, quantum effects that are normally negligible become important. A complete theory of quantum gravity might resolve the singularity, replacing the infinite density with something more physically reasonable. But we don't have a complete theory of quantum gravity. Despite decades of effort, physicists have been unable to successfully combine general relativity with quantum mechanics. The singularity remains a mathematical prediction that we can neither confirm nor resolve. It stands as a monument to the limits of human knowledge, a reminder that even our most successful theories have boundaries beyond which they cannot venture. The singularity forces us to confront uncomfortable questions about the nature of reality itself. If the universe contains regions where our best theories break down, what does that say about the reliability of our understanding? If mathematics itself becomes meaningless at the singularity, how can we trust it to describe the rest of the universe? There's something both humbling and beautiful about a moment of intellectual honesty. It's the moment when a student says, "I don't understand," when a teacher admits, "I don't know," when a scientist confronts the limits of human knowledge and says our equations stop working here. The singularity at the center of black holes represents exactly this kind of moment for physics, a place where our most sophisticated theories raise their hands in defeat and make an honest confession: we have no idea what's really happening. This confession is written in the language of mathematics itself. When physicists solve Einstein's equations for the interior of a black hole, they don't get a neat answer that describes the physics at the center. Instead, they get mathematical infinities, quantities that are undefined, unmeasurable, and essentially meaningless. It's as if the equations are trying to tell us something profound. I was never designed to handle conditions this extreme. The appearance of infinities in physics is usually a red flag. It signals that a theory has been pushed beyond its natural boundaries, into territory where its assumptions no longer hold. It's like using a ruler to measure the distance to the moon. The tool simply isn't appropriate for the task. When infinities appear in physical equations, they're usually telling us that we need better tools, more sophisticated theories, or a fundamentally different approach to the problem. In the case of black hole singularities, the infinities appear in the most fundamental quantities of physics. The density of matter becomes infinite. The curvature of space-time becomes infinite. The tidal forces become infinite. These aren't just big numbers. They're mathematical expressions that have no finite value. They represent the complete breakdown of our ability to describe physical reality. What makes this confession particularly striking is that it comes from general relativity itself. This isn't an external criticism of Einstein's theory. It's the theory's own internal admission of failure. General relativity predicts the existence of singularities, but it also predicts that its own equations become meaningless at those very singularities. It's as if the theory contains a built-in disclaimer: I work everywhere except at the most important points. This self-referential breakdown is unprecedented in physics. Other theories have failed when confronted with new phenomena, but they usually fail because they give wrong answers, not because they give no answers at all. Classical mechanics failed to explain the photoelectric effect, but it still gave predictions that could be tested. General relativity fails at singularities by giving predictions that are literally meaningless. The honesty of this confession is both admirable and troubling. It's admirable because it represents the scientific method at its best, the willingness to acknowledge ignorance and to recognize the limits of our knowledge. It's troubling because it suggests that there might be aspects of reality that are fundamentally beyond our ability to understand or describe. Some physicists have tried to soften this confession by arguing that singularities are not real physical objects, but rather mathematical artifacts that will disappear when we develop better theories. They suggest that the infinities are just a sign that general relativity is incomplete, that a more complete theory of quantum gravity will resolve the singularities and restore mathematical sanity to the center of black holes. But this hopeful interpretation faces serious challenges. For one thing, we don't have a complete theory of quantum gravity, despite decades of effort by brilliant physicists around the world. For another, it's not clear that quantum effects will necessarily resolve the singularities. They might just replace one kind of incomprehensibility with another. The confession of ignorance at the singularity also raises profound questions about the nature of scientific knowledge itself. If our best theories break down at the most extreme conditions in the universe, what does that say about their validity in less extreme conditions? If general relativity fails at singularities, can we trust it to describe the rest of spacetime? These questions don't have easy answers. Science is built on the assumption that the universe is rational and comprehensible, that natural phenomena can be understood through careful observation and mathematical analysis. But the singularity suggests that this assumption might have limits. There might be aspects of reality that are genuinely beyond human comprehension. The honest confession of physics at the singularity also reveals something beautiful about the scientific enterprise. Unlike other ways of understanding the world, science is willing to admit its failures and limitations. It doesn't claim to have all the answers, and it doesn't pretend to understand what it doesn't understand. When confronted with the incomprehensible, science says, "I don't know," and that honesty is perhaps more valuable than any false certainty. This confession of ignorance is not a sign of weakness, but of strength. It represents the humility that is essential to scientific progress. By acknowledging what we don't know, we open the door to new discoveries and new understanding. By admitting that our theories have limits, we create space for better theories to emerge. The singularity stands as a monument to the limits of human knowledge, but also as a challenge to future generations of physicists. It's a problem that demands new approaches, new theories, and new ways of thinking about the nature of reality. It's a reminder that the universe is far stranger and more complex than we can imagine, and that the quest to understand it is far from over. In the world of physics, there are few quests as ambitious or as frustrating as the search for a theory of quantum gravity. It's the scientific equivalent of searching for the Holy Grail, or a theoretical framework that would unite our understanding of the very large and the very small, explaining how gravity works at quantum scales and potentially resolving the mysteries of black hole singularities. Stunk-Fourier, Boulford-Dewey. For nearly a century, brilliant minds have devoted their careers to this quest, and yet we remain tantalizingly far from the goal. The need for quantum gravity becomes apparent when we consider the conditions at the center of a black hole. As matter collapses toward the singularity, it gets compressed into smaller and smaller volumes. Eventually, the matter should be compressed to sizes where quantum effects become important, distances smaller than the Planck length, about 10 circumflex 35 meters. At these scales, the smooth geometry of space-time, described by general relativity, should give way to something far more exotic and quantum mechanical. Imagine trying to zoom in on a smooth painting. From a distance, it looks perfectly continuous and smooth, but as you get closer, you begin to see the individual brushstrokes. Zoom in further, and you see the texture of the canvas. At even higher magnification, you might see the individual fibers of the canvas, and eventually the molecular structure of the paint itself. Similarly, space-time appears smooth at large scales, but at the Planck scale, it should reveal a quantum structure that we don't yet understand. The quest for quantum gravity has produced several promising approaches, each with its own insights and limitations. String theory, perhaps the most famous attempt, proposes that the fundamental building blocks of reality are not point particles, but tiny vibrating strings. These strings exist in a universe with extra dimensions beyond the familiar three of space and one of time. The different vibration patterns of these strings correspond to different particles and forces. String theory is mathematically beautiful and has provided deep insights into the nature of quantum field theory and gravity. It suggests that the singularity at the center of a black hole might be resolved by stringy effects, the finite size of strings, preventing the complete collapse to a point. But string theory faces significant challenges. It requires extra dimensions that we can't observe, and it makes predictions that are difficult or impossible to test experimentally. Loop quantum gravity takes a different approach, attempting to quantize space-time itself. This theory proposes that space is not continuous, but is made up of discrete quantum units. Like pixels in a digital image, at the Planck scale, space-time would have a granular structure, with fundamental units of area and volume that cannot be subdivided further. Loop quantum gravity offers a more direct approach to quantizing general relativity, and it makes specific predictions about what happens at the center of black holes. According to this theory, the singularity is replaced by a quantum bounce, a region where the collapse of matter reverses, potentially creating a new expanding region of space-time. But loop quantum gravity faces its own challenges, including difficulties in recovering the smooth space-time of general relativity at large scales. Other approaches to quantum gravity include causal dynamical triangulation, which builds space-time from geometric building blocks, emergent gravity theories, which suggest that gravity might not be fundamental, but rather an emergent property of more basic phenomena, and various approaches based on holography, and the idea that the information in a volume of space can be encoded on its boundary. Each of these approaches offers tantalizing hints about the nature of quantum gravity, but none has yet provided a complete and convincing theory. The problem is not just technical but conceptual. We're trying to understand a realm of physics where our most basic concepts, space, time, matter, and energy, the quest for quantum gravity is made more challenging by the fact that it's nearly impossible to test these theories experimentally. The energy scales where quantum gravity effects become important are far beyond what we can achieve in any conceivable experiment. We can't create black holes in the laboratory, and we can't directly observe the quantum structure of space-time. This creates an unusual situation in physics. We're trying to develop a theory of phenomena that we can't directly observe or experiment with. We must rely on mathematical consistency, theoretical elegance, and indirect evidence to guide us. It's like trying to understand the nature of light while being permanently blindfolded. Despite these challenges, the quest for quantum gravity continues to drive some of the most creative and ambitious research in physics. The potential rewards are enormous. A complete theory of quantum gravity would not only resolve the singularity problem, but might also explain the nature of dark matter and dark energy, the origin of the universe, and the fundamental structure of reality itself. The search for quantum gravity also represents something profound about the human spirit. It's a quest driven not by practical necessity, but by pure curiosity and the desire to understand. We seek to understand black hole singularities, not because we need to for survival or technology, but because the mystery calls to something deep within us. The same impulse that led our ancestors to wonder about the stars, and that drives us to explore the unknown. Whether we will ever find a complete theory of quantum gravity remains an open question, but the quest itself has already taught us much about the nature of space, time, and reality. It has shown us that the universe is far stranger and more complex than we ever imagined, and that the boundaries of human knowledge are still expanding. Imagine approaching what appears to be an open doorway, only to discover at the last moment that it's actually a wall of fire. This is the essence of the firewall hypothesis, one of the most dramatic and controversial proposals in modern physics. According to this idea, the event horizon of a black hole, which should be an invisible and harmless boundary according to general relativity, is actually a barrier of destruction that would instantly incinerate anything attempting to cross it. The firewall hypothesis emerged from the desperate attempt to resolve the information paradox. If information cannot be destroyed, as quantum mechanics demands, then something must prevent information from falling into black holes, where it would be lost forever. The firewall represents the most extreme solution to this problem, a proposal that the event horizon is not empty space, but a wall of highly energetic particles that would destroy any approaching matter. The idea sounds almost absurd at first. General relativity tells us that the event horizon is not a physical barrier, but simply a coordinate boundary, a point of no return, but not a point of destruction. An observer falling into a black hole should pass through the event horizon without noticing anything special. The transition should be smooth and uneventful, like crossing an invisible line drawn on the surface of a calm ocean. But the firewall hypothesis suggests that this smooth passage is impossible if we want to preserve quantum mechanical principles. If information falling into a black hole must somehow be preserved, then the event horizon cannot be the peaceful boundary that general relativity describes. Instead, it must be a region of violent quantum activity, where the very fabric of space-time is torn apart by the conflicting demands of general relativity and quantum mechanics. The physics behind the firewall is rooted in the peculiar properties of quantum entanglement. When particles are entangled, they share a mysterious connection that Einstein famously called spooky action at a distance. The quantum state of one particle is instantly correlated with the state of its entangled partner, regardless of the distance between them. This correlation is so strong that measuring one particle immediately affects the other, even if they are separated by vast distances. The firewall hypothesis suggests that Hawking radiation particles escaping from a black hole must be entangled with particles inside the black hole to preserve information. But quantum mechanics places strict limits on how particles can be entangled. A particle can be strongly entangled with, at most, one other particle. If it becomes entangled with a second particle, its entanglement with the first particle must be broken. This creates what physicists call the monogamy of entanglement. Like a monogamous relationship, strong quantum entanglement cannot be shared among multiple partners. If a Hawking radiation particle is entangled with a particle inside the black hole to preserve information, it cannot also be entangled with its partner particle at the event horizon. The entanglement that allows smooth passage through the event horizon must be severed. When quantum entanglement is broken, energy is released. In the case of the firewall, this energy release would be catastrophic. The breaking of entanglement between particles at the event horizon would create a wall of high-energy particles, a firewall that would destroy anything attempting to cross the boundary. The peaceful event horizon becomes a cosmic furnace. The firewall hypothesis represents a radical departure from our understanding of black holes. It suggests that the event horizon is not an invisible boundary, but a visible, destructive barrier. It means that black holes would literally burn up anything that falls into them, not through gravitational crushing, but through quantum incineration. The elegant picture of smooth space-time curvature is replaced by a violent quantum demolition zone. This proposal has profound implications for our understanding of space and time. If the firewall hypothesis is correct, then general relativity's prediction of smooth space-time geometry is fundamentally wrong. The curvature of space-time cannot be smooth and continuous if it contains regions of violent quantum activity. The geometric picture of gravity must give way to something more complex and violent. The firewall also raises disturbing questions about the nature of the event horizon itself. If the event horizon is a wall of destruction, then it's no longer a point of no return, but a point of no survival. Nothing could cross the firewall and continue existing. The firewall also raises disturbing questions about the nature of the event horizon itself. The black hole would consume matter, not by gravitational capture, but by quantum annihilation. But the firewall hypothesis faces serious challenges. Most importantly, it violates the equivalence principle, one of the fundamental principles of general relativity. This principle states that there's no difference between being in a gravitational field and being in an accelerated reference frame. If the firewall exists, then a freely falling observer would be able to detect the presence of the gravitational field by encountering the destructive barrier. The firewall also creates new paradoxes. If the event horizon is a wall of destruction, then how can black holes grow by consuming matter? How can they merge with other black holes? The firewall seems to prevent the very processes that we observe in the universe. Despite these challenges, the firewall hypothesis has forced physicists to confront the fundamental incompatibility between general relativity and quantum mechanics. It represents the most dramatic attempt to resolve the information paradox, even if it requires us to abandon some of our most cherished assumptions about the nature of space-time. The firewall controversy continues to divide the physics community. Some see it as a necessary consequence of preserving quantum mechanics. Others view it as a sign that we need entirely new approaches to understanding black holes. But everyone agrees that it represents a profound challenge to our understanding of reality. In the quiet moments of scientific contemplation, physicists sometimes find themselves facing impossible choices, moments when the universe seems to offer only unacceptable alternatives. The firewall controversy represents exactly such a moment, presenting us with a trilemma where every option requires abandoning something fundamental about our understanding of reality. It's like being forced to choose between losing your memory, your identity, or your ability to reason. Each choice is devastating in its own way. The impossible choice at the heart of the firewall controversy can be stated simply. We cannot simultaneously preserve three principles that seem essential to physics. We cannot have smooth event horizons, preserve quantum information, and maintain the validity of quantum field theory. Like a cosmic game of rock, paper, scissors, each principle defeats one of the others, leaving us with no winning combination. The first principle is the smoothness of event horizons, derived from general relativity's equivalence principle. This principle states that a freely falling observer cannot detect the presence of a gravitational field through local experiments. Injursealing feu, theory of thing. Applied to black holes, this means that someone falling through an event horizon should experience nothing special, no barrier, no firewall, no moment of destruction. The passage should be as smooth and uneventful as floating through empty space. This principle has deep philosophical importance. It suggests that the laws of physics are the same everywhere in the universe, that there are no special places where the fundamental rules change. It implies that the universe is fundamentally democratic, that the same physical laws apply to every observer, regardless of their location or circumstances. To abandon this principle would be to accept that the universe has privileged locations where different physics applies. The second principle is the preservation of quantum information. This principle states that information cannot be created or destroyed, only transformed. Every quantum interaction preserves all the information about the initial state in the final state, even if that information becomes scrambled or difficult to extract. This principle is fundamental to quantum mechanics and underlies our understanding of everything from atomic structure to quantum computing. Information preservation is not just a technical requirement, but a philosophical cornerstone of our understanding of reality. It suggests that the universe has a perfect memory, that every event leaves an indelible mark on the quantum state of the cosmos. To abandon this principle would be to accept that the past can be erased, that the universe is fundamentally forgetful. The third principle is the validity of quantum field theory in curved spacetime. This principle states that the quantum mechanical description of particle creation and annihilation works the same way in curved spacetime as it does in flat spacetime. It's the foundation of our understanding of Hawking radiation and the quantum mechanics of black holes. This principle is essential to our understanding of the early universe, where quantum fields evolved in the curved spacetime created by cosmic expansion. It underlies our theories of inflation, dark matter, and the formation of the first structures in the universe. To abandon this principle would be to lose our quantum understanding of cosmology. Firewall controversy arises because these three principles appear to be mutually incompatible. If we insist on preserving quantum information, then Hawking radiation particles must be entangled with particles inside the black hole. But quantum field theory limits how particles can be entangled. A particle cannot be strongly entangled with multiple partners simultaneously. If the Hawking radiation is entangled with the interior, it cannot also be entangled with its partner at the event horizon. This forces us to choose. If we preserve information and accept quantum field theory, then we must abandon the smooth event horizon. The result is the firewall, a wall of destruction that incinerates anything attempting to cross the boundary. The equivalence principle is violated, and general relativity's prediction of smooth spacetime geometry is wrong. Alternatively, if we insist on preserving the smooth event horizon and accepting quantum field theory, then we must abandon information preservation. The information that falls into black holes is truly lost, violating quantum mechanics. The universe becomes forgetful, and the foundations of quantum theory crumble. A third option is to preserve information and maintain smooth event horizons while abandoning quantum field theory in curved spacetime. This would require a fundamental revision of our understanding of quantum mechanics in gravitational fields. The familiar rules of particle creation and annihilation would need to be replaced by something entirely new. Each choice is devastating. The smooth event horizon is not just a technical prediction, but a fundamental aspect of how we understand space and time. Information preservation is not just a quantum principle, but a philosophical foundation of our belief in the rationality of the universe. Quantum field theory is not just a mathematical framework, but the basis of our understanding of particle physics and cosmology. The impossible choice reveals something profound about the nature of scientific progress. Sometimes advancement requires not just discovering new facts, but abandoning old certainties. The firewall controversy is forcing physicists to question their most basic assumptions about reality. But perhaps the most unsettling aspect of this impossible choice is that it might not have a resolution. We might be forced to accept that the universe is fundamentally inconsistent, that there are aspects of reality that cannot be reconciled with our rational understanding. The firewall controversy might be showing us the limits of human comprehension, the boundaries beyond which our logic and mathematics cannot venture. The choice remains before us, stark and uncompromising. We can preserve our understanding of space-time, our faith in quantum mechanics, or our grasp of quantum field theory, but we cannot preserve all three. The universe seems to be asking us to choose what we value most about our understanding of reality. There's a peculiar curse that seems to haunt the deepest problems in physics. Every solution creates new problems. It's as if the universe has a perverse sense of humor, offering answers that raise more questions than they resolve. The firewall controversy exemplifies this curse perfectly. Every proposed resolution to the information paradox seems to create new paradoxes that are just as troubling as the original problem. The history of attempts to resolve the firewall paradox reads like a catalogue of ingenious ideas that transform into new impossibilities. Each proposed solution initially appears promising, offering a way to preserve our cherished principles while avoiding the violent destruction at the event horizon. But upon closer examination, each solution reveals its own contradictions, its own violations of physical principles, its own impossible implications. Consider the complementarity principle, proposed by some physicists, as a way to resolve the paradox without firewalls. This principle suggests that the information paradox is not a real contradiction, but rather a consequence of asking the wrong questions. According to complementarity, the information both falls into the black hole and escapes with the Hawking radiation, but these two descriptions apply to different observers and can never be compared directly. From the perspective of an outside observer, the information never actually crosses the event horizon, but remains encoded in the increasingly redshifted radiation at the boundary. From the perspective of an infiling observer, the information smoothly crosses the event horizon and falls toward the singularity. These two descriptions are complementary, like wave and particle descriptions of light. Both are true, but they apply to different experimental situations. Complementarity seems to offer a way out of the firewall paradox. If the information is preserved from the outside perspective, and the event horizon is smooth from the inside perspective, then we don't need to choose between them. We can have both information preservation and smooth event horizons, as long as we never try to compare them directly. but complementarity creates its own problems. If the two descriptions can never be compared, then physics becomes fundamentally subjective. Different observers would live in different realities, with no way to reconcile their experiences. The objective reality that science seeks to understand would be replaced by multiple, mutually incompatible realities. This seems to abandon the very foundation of scientific inquiry. Another proposed solution involves the holographic principle, which suggests that all the information in a volume of space can be encoded on its boundary. Applied to black holes, this principle suggests that the information that appears to fall into the black hole is actually encoded on the event horizon surface. The information is never truly lost, because it's always present at the boundary. The holographic principle has deep connections to string theory and has been successful in other areas of physics. It offers a way to preserve information without requiring firewalls or abandoning general relativity. The event horizon becomes a cosmic hard drive, storing all the information that has ever approached the black hole in a scrambled but recoverable form. But the holographic solution faces its own challenges. If the information is encoded on the event horizon, then the horizon cannot be empty space as general relativity suggests. It must have a complex structure capable of storing enormous amounts of information. This seems to violate the principle that nothing special happens at the event horizon. More seriously, the holographic principle requires that the information be encoded in a way that preserves all quantum correlations. This encoding must be so perfect that it captures not just the gross properties of the infalling matter, but every quantum detail. The computational requirements for such encoding seem to exceed what's possible in the available time and space. Yet another approach involves modifying quantum mechanics itself. Some physicists have proposed that information can be destroyed in black holes, but only in ways that preserve the essential consistency of quantum theory. These proposals typically involve tiny violations of quantum mechanics that would be undetectable in ordinary circumstances, but would become important in the extreme environment of black holes. These modifications of quantum mechanics seem to offer a way to preserve general relativity while avoiding the firewall paradox. If information can be destroyed in black holes, then there's no need for the complex entanglement structures that lead to firewalls. The event horizon can remain smooth and uneventful. But modifying quantum mechanics is extraordinarily difficult. The theory is so tightly constrained by experimental tests that almost any change threatens to create contradictions with known results. The modifications must be incredibly subtle and carefully crafted to avoid disrupting the quantum mechanical predictions that have been verified countless times. Perhaps most troubling is the meta-problem that emerges from this parade of failed solutions. Every proposed resolution of the firewall paradox seems to create new problems that are just as severe as the original problem. This suggests that the paradox might not be a technical issue that can be resolved with clever physics, but rather a fundamental limitation of our approach to understanding reality. The paradox of solutions forces us to confront the possibility that some problems in physics might not have solutions at all. They might be indicators that our theoretical framework is fundamentally incomplete, or that reality itself is more complex than our human minds can grasp. The firewall controversy might be showing us the boundaries of scientific knowledge, the limits beyond which our logic and mathematics cannot venture. This realization is both humbling and liberating. It's humbling because it suggests that there are aspects of the universe that might be forever beyond our comprehension. But it's also liberating because it frees us from the assumption that every problem must have a solution, that every paradox must be resolved. Sometimes the most profound insights come not from solving problems, but from understanding why they cannot be solved. Imagine that everything you've ever known about the fundamental nature of reality is wrong. Imagine that the particles you think of as tiny point-like objects are actually microscopic strings, vibrating in dimensions you cannot see. Imagine that the entire universe is like a vast cosmic symphony, where every note is played by strings so small that they make atoms look like galaxies. This is the audacious vision of string theory, perhaps the most ambitious attempt in human history to understand the deepest secrets of existence. String theory emerged from the recognition that our current theories of physics are fundamentally incomplete. While general relativity beautifully describes gravity and the large-scale structure of the universe, and quantum mechanics perfectly explains the behavior of atoms and subatomic particles, these two theories are mathematically incompatible. They give different answers to questions about what happens in extreme conditions, like the center of black holes or the first moments after the Big Bang. The central insight of string theory is breathtakingly simple. What if the fundamental constituents of reality are not particles, but strings? These strings are unimaginably small, about 10 circumflex 35 meters long, so tiny that if you scaled an atom up to the size of our solar system, a string would still be smaller than a tree. These strings can vibrate in different patterns, and each pattern of vibration corresponds to a different particle. Think of a violin string. Depending on how you pluck it, bow it, or press it, the same string can produce different musical notes. Similarly, a fundamental string can vibrate in different modes, creating what we perceive as different particles. An electron might be a string vibrating in one pattern. A photon might be the same string vibrating in another pattern. And a graviton, the hypothetical particle that carries gravitational force, might be yet another vibration pattern. This musical metaphor isn't just poetic, it's mathematically precise. The equations of string theory describe how these cosmic strings vibrate, interact, and create the rich tapestry of particles and forces that make up our universe. Every particle in the standard model of physics, every force that shapes reality, every field that permeates space, all of it emerges from the vibrations of these fundamental strings. But string theory demands something extraordinary from us. It requires us to accept that space has more dimensions than we can perceive. While we experience 3 dimensions of space and 1 of time, string theory typically requires 10 or 11 dimensions for mathematical consistency. The extra dimensions are hidden from us, curled up so tightly that they're invisible at everyday scales. Imagine walking along a tightrope, high above the ground. From a distance, the rope looks like a one-dimensional line, but if you could zoom in close enough, you'd see that the rope actually has thickness. It extends in dimensions that are invisible from far away. Similarly, string theory suggests that what we perceive as 3-dimensional space is actually a higher dimensional reality, where the extra dimensions are curled up too small for us to detect. These hidden dimensions are not just mathematical curiosities. They're essential to string theory's potential to resolve the black hole information paradox. The extra dimensions provide new ways for information to be stored and processed. They offer escape routes for information that appears to be trapped behind event horizons. They create geometric structures that could prevent the formation of singularities. String theory also predicts the existence of objects called branes, higher dimensional surfaces where strings can end. Our entire universe might be a 3-dimensional brane floating in a higher dimensional space. This brane world scenario opens up possibilities for understanding black holes that are completely unavailable to conventional physics. In the string theory picture, black holes become far more complex and interesting objects. They're not just regions where space-time curves to infinity, but intricate configurations of strings and branes that can store and process information in ways that classical physics cannot describe. The event horizon might not be a boundary where information disappears, but a surface where information is encoded in string vibrations. Some string theorists have proposed that the interior of a black hole might be connected to the exterior through hidden dimensions. Information that appears to fall into the black hole might actually be transmitted through these extra dimensions and emerge in the Hawking radiation. The information would be preserved, but in a form so scrambled and complex that it would be practically impossible to decode. String theory also offers a potential resolution to the singularity problem. In classical general relativity, the center of a black hole is a point of infinite density and curvature. But in string theory, the finite size of strings prevents any truly point-like concentrations of matter. In truly point-like concentrations of matter, the singularity might be replaced by a small but finite string-scale structure, still incredibly dense and curved, but not infinitely so. In truly pointer but insanit saw, sir, into repav. The mathematical beauty of string theory is undeniable. It elegantly unifies all the forces of nature into a single theoretical framework. It provides a quantum mechanical description of gravity. It offers potential solutions to some of the deepest puzzles in physics. Mysterium, Physica. The theory is so mathematically rich that it continues to provide new insights, even decades after its initial development. Facile, 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 facile. But string theory faces significant challenges. Despite its mathematical elegance, it has yet to make a single testable prediction that distinguishes it from other theories. The energy scales where string effects become important are far beyond what we can reach with any conceivable experiment. The theory requires us to accept the existence of extra dimensions and exotic objects that we have never observed. What if everything you think you know about the nature of reality is fundamentally wrong? What if the three-dimensional world you inhabit is actually a projection from a two-dimensional surface, like a hologram created by cosmic forces beyond your comprehension? This is the startling suggestion of the holographic principle, one of the most revolutionary ideas in modern physics, and perhaps our best hope for resolving the paradoxes that plague our understanding of black holes. The holographic principle emerged from a deep puzzle about the nature of information and entropy. In the 1970s, physicists discovered that black holes have entropy, a measure of the disorder or information content of a system. But unlike ordinary objects, where entropy is proportional to volume, black hole entropy is proportional to surface area. This seemed strange and counterintuitive. Why should the information content of a three-dimensional object depend on its two-dimensional surface? The answer, according to the holographic principle, is that the information was never really in the three-dimensional volume to begin with. All the information in any region of space can be encoded on the boundary of that region. Just as a hologram stores a three-dimensional image on a two-dimensional surface, the universe itself might be a holographic projection from a lower dimensional boundary. This idea sounds like science fiction, but it has deep mathematical foundations. The holographic principle has been rigorously developed in the context of string theory, where it's known as the ADS-EFT correspondence. This correspondence shows that certain gravitational theories in higher dimensions are mathematically equivalent to quantum field theories in lower dimensions. The higher dimensional theory describes the bulk of space-time, while the lower dimensional theory describes the boundary. Applied to black holes, the holographic principle suggests a radical reinterpretation of what happens when matter falls past the event horizon. Instead of disappearing into the interior, the information about the falling matter is encoded on the event horizon surface. The black hole becomes like a cosmic hard drive, storing all the information that has ever approached it in a scrambled but recoverable form. From this perspective, the event horizon is not a boundary between the known and unknown, but a surface where all the information in the black hole is stored. The interior of the black hole might not even exist as a separate region of space-time. What we think of as the three-dimensional interior might be nothing more than a holographic projection of the two-dimensional information stored on the event horizon. This holographic view of black holes offers a potential resolution to the information paradox. If the information is always stored on the event horizon surface, then it never truly falls into the black hole. When the black hole evaporates through Hawking radiation, the information can be recovered from the horizon surface. The information is preserved, but in a form so scrambled and complex that it would be practically impossible to decode. The holographic principle also suggests a new way of thinking about the firewall paradox. If the interior of the black hole is a holographic projection of the boundary, then the smooth event horizon and the information-preserving boundary are not separate objects, but different descriptions of the same reality. The apparent contradiction between general relativity and quantum mechanics might be resolved by recognizing that they describe different aspects of the same holographic system. But the holographic principle raises profound questions about the nature of reality itself. If the three-dimensional universe is a projection from a two-dimensional surface, then what is the fundamental nature of space and time? Are the dimensions we experience real, or are they emergent properties of a more fundamental lower-dimensional reality? The implications extend far beyond black holes. If the holographic principle is correct, then the entire universe might be a projection from its cosmic boundary. All the galaxies, stars, planets, and life forms that we observe might be holographic images created by information stored on the edge of the universe. We might be living in a cosmic hologram, unaware that our three-dimensional existence is actually a projection from a two-dimensional reality. This possibility is both fascinating and deeply unsettling. It challenges our most basic assumptions about the nature of existence. It suggests that the world we experience might be fundamentally different from the world that actually exists. It raises the question, if we are holographic projections, are we real in any meaningful sense? The holographic principle also offers new ways of thinking about the relationship between information and space-time. In the holographic view, space-time itself might be an emergent property of information. The geometry of the universe might be determined by the information content of its boundary. Space and time might not be fundamental features of reality, but rather collective properties that emerge from more basic informational structures. This informational view of space-time has profound implications for our understanding of black holes. If space-time is emergent from information, then the extreme curvature near black holes might reflect the complex information processing that occurs at the event horizon. The apparent breakdown of physics at the singularity might be a sign that we're trying to apply concepts of space and time in a regime where they no longer apply. The holographic principle remains speculative, but it has already provided deep insights into the nature of quantum gravity and the structure of space-time. It offers a new framework for understanding black holes that might resolve the paradoxes that have puzzled physicists for decades. It suggests that the universe is far stranger and more wonderful than we ever imagined, a place where three-dimensional reality emerges from two-dimensional information, where the familiar world of space and time is revealed to be a holographic projection of something far more fundamental. There's a peculiar humility that comes with standing at the edge of human knowledge. It's the recognition that even our most sophisticated theories, our most elegant mathematics, our most ambitious intellectual constructions are still incomplete maps of a reality that remains largely mysterious. String theory and the holographic principle represent the furthest reaches of human understanding, the most advanced attempts to comprehend the deepest secrets of existence. Yet even these remarkable achievements leave us with more questions than answers, more mysteries than revelations. String theory, for all its mathematical beauty and theoretical elegance, remains tantalizingly unproven. Despite decades of development by some of the most brilliant minds in physics, the theory has yet to make a single testable prediction that distinguishes it from other approaches to quantum gravity. The energy scales where string effects become important are so far beyond our experimental reach that they might remain forever inaccessible to direct observation. The theory requires us to accept the existence of extra dimensions that we cannot see, particles that we cannot detect, and symmetries that we cannot verify. It demands faith in mathematical beauty as a guide to truth, but the history of science is littered with beautiful theories that turned out to be wrong. The universe is under no obligation to conform to our aesthetic preferences or mathematical intuitions. String theory also faces the troubling problem of landscape. The theory appears to have an enormous number of possible solutions, perhaps 10 circumflex, 500 different ways of configuring the extra dimensions and the fundamental parameters. This vast landscape of possibilities makes it difficult to extract specific predictions from the theory. If almost anything is possible within string theory, then the theory explains nothing. The holographic principle faces its own limitations and challenges. While it has been rigorously established in certain highly symmetric situations, it remains unclear whether it applies to realistic black holes and cosmological scenarios. The mathematical correspondence between higher dimensional gravity and lower dimensional field theory works beautifully in abstract theoretical models, but the real universe is messier and more complex than these idealized scenarios. Moreover, the holographic principle raises profound conceptual questions that we are far from resolving. If reality is truly holographic, then what is the nature of the screen on which it is projected? What determines the information content of the boundary? How does the projection process work? These questions push us to the very limits of our conceptual frameworks. The attempt to apply holographic ideas to black holes also faces practical challenges. If the information falling into a black hole is encoded on the event horizon surface, then the encoding must be incredibly efficient and robust. The surface must be able to store and process information at rates that seem to exceed what's possible with any known physical system. The computational requirements for holographic encoding appear to be beyond what the universe can provide. Both string theory and the holographic principle share a common limitation. They remain largely theoretical constructs with limited connection to observable phenomena. They exist primarily in the realm of mathematical abstraction, beautiful and elegant, but disconnected from the empirical world that science seeks to understand. They represent the triumph of human mathematical creativity, but they may not represent the truth about the physical universe. This disconnect between theory and observation is particularly troubling in the context of black holes. The paradoxes that motivate these theories, the information paradox, the firewall controversy, the singularity problem, arise from theoretical considerations rather than experimental observations. We are trying to solve problems that we have never directly observed, using theories that we cannot directly test. The situation is further complicated by the fact that these theories often make predictions that are impossible to verify. If the information in a black hole is encoded holographically on the event horizon, we could never decode it to verify that the encoding is actually happening. If strings are the fundamental constituents of reality, they are too small to ever be observed directly. We find ourselves in the strange position of developing theories that are, in principle, unverifiable. This raises profound questions about the nature of scientific progress and the limits of human knowledge. Are we approaching the boundaries of what can be known through scientific inquiry? Are we developing theories that are so removed from empirical reality that they cease to be science in any meaningful sense? Are we constructing elaborate mathematical edifices that tell us more about the structure of human thought than about the structure of reality? The limitations of our best theories also highlight the provisional nature of all scientific knowledge. String theory and the holographic principle represent the current frontier of our understanding, but they are not final truths. They are working hypotheses, conceptual frameworks that might be abandoned or radically revised as our understanding deepens. The history of science is a history of theories that were once considered fundamental, but were later revealed to be approximations or special cases of more general principles. Perhaps most importantly, the limitations of our theories remind us that the universe is under no obligation to be comprehensible to human minds. The problems we face in understanding black holes might not be merely technical challenges that can be overcome with better theories and more sophisticated mathematics. They might be fundamental limitations of human cognition, boundaries beyond which our evolved brains cannot venture. The recognition of these limitations is not a cause for despair but for wonder. It reminds us that the universe is far stranger and more complex than we can imagine. It suggests that the quest to understand reality will continue long after our current theories have been forgotten. It reveals that the deepest mysteries of existence remain unsolved, waiting for future generations to discover new ways of thinking about the cosmos. There's a moment in every great intellectual journey when you realize that the mountain you've been climbing is not a peak, but a foothill, and that the true summit disappears into clouds beyond your ability to see. Black holes represent exactly this moment for human physics, a cosmic mirror that reflects back not our knowledge, but our ignorance. They are the universe's way of whispering, with perfect gentleness, "You understand far less than you think you do." This humbling is not a failure, but a gift. For centuries, humanity has been on an extraordinary winning streak in understanding the natural world. We decoded the motion of planets, unraveled the secrets of atoms, harnessed the power of electricity and magnetism, split the nucleus, and peered into the genetic code of life itself. Each victory built our confidence. Each success suggested that the universe was fundamentally comprehensible, that with enough cleverness and persistence, we could eventually understand everything. Black holes shatter this confidence in the most beautiful way possible. They present us with phenomena that our best theories cannot explain, questions that our most sophisticated mathematics cannot answer, paradoxes that our most careful reasoning cannot resolve. They are cosmic teachers, using the language of impossibility to show us that the universe is far stranger, far more complex, and far more wonderful than we ever dared imagine. The specific nature of this humbling is particularly profound. Black holes don't just present us with new phenomena to study. They present us with the breakdown of our most fundamental concepts. They show us that space and time, the very stage on which we thought all physics played out, are themselves actors in a drama we don't understand. They reveal that information, which we thought was sacred and indestructible, might be subject to rules we haven't discovered. They demonstrate that causality itself becomes ambiguous in the extreme conditions they create. This isn't the humbling of a student who gets a difficult problem wrong. This is the humbling of discovering that the language in which we've been trying to understand the universe might be fundamentally inadequate. It's like a poet realizing that the deepest truths cannot be captured in words, or a musician discovering that the most beautiful melodies exist in frequencies beyond human hearing. The humbling extends beyond the technical details of physics to our most basic assumptions about the nature of knowledge itself. We've built science on the assumption that the universe is rational, that natural phenomena follow logical rules that can be discovered through careful observation and reasoning. Black holes suggest that this assumption might have limits. They point to aspects of reality that might be genuinely unknowable, not just difficult to understand, but fundamentally beyond the reach of human comprehension. This possibility is both terrifying and liberating. It's terrifying because it suggests that our quest to understand the universe might be doomed to incompleteness. It's liberating because it frees us from the burden of having to explain everything, from the assumption that every mystery must have a solution within our current conceptual framework. The humbling also comes with a profound sense of wonder. Black holes don't just show us the limits of our knowledge, they reveal the extraordinary richness of the unknown. They suggest that the universe contains depths of mystery that we haven't even begun to explore. They point to realms of reality that might be so strange and complex that they require entirely new forms of understanding. This wonder is not just intellectual but deeply aesthetic. There's something beautiful about the way black holes challenge our understanding, something elegant about the way they reveal the inadequacy of our theories. They represent the universe at its most mysterious and poetic, regions where the familiar laws of physics dissolve into something far more strange and wonderful. The humbling also carries practical implications for how we do science. It suggests that we should hold our theories more lightly, be more open to radical revisions of our understanding, and be more comfortable with uncertainty and ignorance. It reminds us that science is not a process of accumulating final truths, but of constructing provisional maps of reality that are always subject to revision. Perhaps most importantly, the humbling teaches us something about our place in the universe. We are not cosmic masters, destined to understand and control everything. We are cosmic explorers, privileged to glimpse the edges of mysteries that extend far beyond our current understanding. We are participants in a grand adventure of discovery, not conquerors of a universe that must yield to our intellectual demands. The wisdom of cosmic humility is not about giving up on understanding, but about holding that understanding more lightly. It's about recognizing that the universe is under no obligation to make sense to us, that our theories are tools rather than truths, and that the greatest discoveries often come from recognizing the limits of what we know. Black holes teach us that the universe is far stranger than we can imagine, and perhaps stranger than we can imagine. They remind us that the deepest questions about reality remain unanswered, that the most profound mysteries are still waiting to be explored. They show us that the frontier of human knowledge is not a destination, but a journey, not a place to arrive, but a direction to travel. In the end, the humbling beauty of black holes lies not in their ability to confound our understanding, but in their capacity to inspire our wonder. They remind us that we live in a universe full of mysteries, a cosmos that continues to surprise and challenge us. In the end, the humbling beauty of black holes lies not in their ability to confound our understanding. They show us that the quest to understand reality is not a problem to be solved, but an adventure to be embraced, not a destination to reach, but a journey to cherish. Hole. When we gaze into the heart of a black hole, we're not just looking at an extreme astrophysical object, we're confronting the deepest philosophical questions about the nature of reality itself. These cosmic monsters force us to ask not just, how does the universe work, but what does it mean for the universe to work at all? They push us beyond the comfortable realm of scientific facts, into the unsettling territory of fundamental metaphysics, where the boundaries between physics and philosophy dissolve like matter crossing an event horizon. The philosophical implications of black holes begin with the most basic question: what is real? In our everyday experience, reality seems solid and unambiguous. Objects have definite locations, events occur in a clear sequence, and the past is fixed while the future is open. But near black holes, even these basic assumptions crumble. Time becomes relative, simultaneity becomes meaningless, and the very concept of now loses its universal significance. This relativity of experience raises profound questions about the nature of truth itself. If different observers see contradictory realities near black holes, one seeing matter frozen at the event horizon, while another sees it smoothly crossing, then which version is true? The traditional scientific answer is that both are true within their respective reference frames. But this answer leads to a deeper philosophical puzzle. If multiple contradictory descriptions of the same event can all be true, then what does truth even mean? The information paradox pushes these questions even further. If information can be destroyed in black holes, then the universe's memory is imperfect. The past can be erased, leaving no trace of what once was. This possibility challenges our most basic assumptions about causality and determinism. If the present state of the universe doesn't uniquely determine its past, then the arrow of time becomes ambiguous. The future might be open not just because it hasn't happened yet, but because the past itself might be changeable. The firewall controversy reveals another philosophical dimension, the problem of multiple realities. If the event horizon is simultaneously smooth and filled with destructive firewalls, depending on your perspective, then reality itself becomes observer-dependent. This isn't just a matter of measurement or perception, it's a fundamental feature of how the universe is structured. Different observers don't just see different aspects of the same reality, they literally inhabit different realities. This multiplicity of realities challenges the core assumption of science, that there is an objective reality that exists independently of observers. If reality is genuinely observer-dependent, then the scientific quest to understand the universe becomes meaningless. There might not be a single universe to understand, but rather a collection of realities that cannot be reconciled with each other. The singularity problem raises perhaps the most profound philosophical question of all. What happens when the very concepts we use to understand reality break down? At the center of a black hole, our mathematical descriptions of space, time, and matter become meaningless. We encounter infinities that cannot be interpreted, equations that cannot be solved, and conditions that cannot be described. This breakdown isn't just a technical problem, it's a crisis of meaning. If our most fundamental concepts fail to apply in certain regions of the universe, then what does it mean to say we understand the universe at all? The singularity suggests that there might be aspects of reality that are genuinely beyond human comprehension, not just difficult to understand, but literally incomprehensible. The philosophical implications extend to our understanding of knowledge itself. Science is built on the assumption that the universe is rational and comprehensible, that natural phenomena follow logical rules that can be discovered through careful observation and reasoning. But black holes suggest that this assumption might have limits. They point to aspects of reality that might be genuinely unknowable, not just practically difficult to study, but fundamentally beyond the reach of rational inquiry. This possibility raises the question of whether there are limits to human knowledge. Are we approaching the boundaries of what can be known through scientific investigation? Are we discovering that the universe contains mysteries that are deeper than our capacity to understand them? The confrontation with these limits is both humbling and awe-inspiring. The philosophical challenges of black holes also touch on questions of existence and identity. If the universe is fundamentally observer-dependent, then what does it mean to exist? If reality is multiple and contradictory, then how do we understand our own place within it? If the past can be erased and the future is undetermined, then what gives meaning to our present existence? These questions don't have easy answers. They push us to the very limits of human understanding, to the boundaries where physics meets philosophy and where rational inquiry encounters the ineffable. They remind us that the universe is not just a collection of objects and forces, but a profound mystery that challenges our deepest assumptions about the nature of reality. Perhaps the most beautiful aspect of these philosophical challenges is that they keep the sense of wonder alive in science. They remind us that despite all our technological achievements and theoretical sophistication, we are still cosmic explorers confronting mysteries that dwarf our understanding. They show us that the universe is not a puzzle to be solved, but a mystery to be experienced, not a problem to be conquered, but a source of endless fascination. The philosophy of cosmic mystery suggests that the deepest questions about reality might not have answers in any conventional sense. They might be questions that transform us in the very act of asking them. Mysteries that change us rather than yielding to our understanding. In confronting the philosophical implications of black holes, we don't just learn about the universe, we discover new depths of wonder and humility that enrich our human experience. The story of black holes is not ending, it's just beginning. Despite decades of theoretical work and countless brilliant insights, we remain at the very beginning of our understanding of these cosmic enigmas. They continue to challenge our most basic assumptions about reality, to reveal new depths of mystery with each theoretical advance, and to inspire new generations of physicists to push the boundaries of human knowledge. In many ways, black holes represent the eternal nature of scientific inquiry itself, a quest that deepens rather than diminishes as we learn more. The technological revolution that is just beginning will bring new tools to bear on these ancient mysteries. The Event Horizon Telescope has already given us our first direct images of black holes, revealing the shadow cast by the event horizon against the glowing backdrop of infalling matter. These images are not just beautiful, they're the first direct observational evidence of the event horizon itself, the boundary that has been purely theoretical for so long. Future technological advances promise even more dramatic revelations. Gravitational wave detectors are becoming increasingly sensitive, allowing us to observe the collisions and mergers of black holes in real time. These cosmic catastrophes create ripples in space-time itself, carrying information about the internal structure of black holes and the nature of strongly curved space-time. We are literally listening to the universe sing the songs of black holes. Space-based gravitational wave detectors, currently in development, will be able to observe black hole mergers with unprecedented precision. They will detect the subtle variations in gravitational waves that might reveal whether black holes have the smooth event horizons that general relativity predicts, or the complex structures that quantum theories suggest. These observations might finally resolve some of the paradoxes that have puzzled physicists for decades. Quantum technologies are also opening new avenues for understanding black holes. Quantum computers might be able to simulate the complex quantum mechanical processes that occur near event horizons, allowing us to explore scenarios that are impossible to study analytically. Quantum error correction techniques might provide insights into how information is preserved and processed in extreme gravitational fields. the theoretical landscape is equally rich with possibilities. New approaches to quantum gravity are being developed that might resolve the long-standing conflict between general relativity and quantum mechanics. Loop quantum gravity, causal dynamical triangulation, asymptotic safety, and other approaches each offer different perspectives on how spacetime might behave at the smallest scales. One of these approaches, or perhaps a completely new idea, might finally explain what happens at the center of black holes. String theory continues to evolve, with new mathematical techniques revealing unexpected connections between black holes and other areas of physics. The holographic principle has led to deep insights into the nature of spacetime and information, suggesting that our three-dimensional reality might be a projection from a two-dimensional surface. These ideas are still speculative, but they point toward a radically different understanding of the fundamental nature of reality. The quest to understand black holes is also driving advances in other areas of physics. The study of quantum entanglement, motivated partly by black hole information paradoxes, has led to breakthroughs in quantum computing and quantum cryptography. The exploration of holographic principles has revealed new connections between condensed matter physics and gravity. The attempt to understand the firewall paradox has deepened our understanding of the relationship between geometry and information. Perhaps most importantly, the study of black holes continues to inspire new ways of thinking about the deepest questions in physics. They force us to confront the limits of our current theories and to imagine new conceptual frameworks that might transcend those limits. They challenge us to think beyond the boundaries of our current understanding and to consider possibilities that seem impossible from our current perspective. The eternal nature of this quest is perhaps its most beautiful aspect. Each answer we discover about black holes leads to new questions. Each mystery we solve reveals new mysteries. Each theoretical advance opens up new territories of ignorance that we didn't even know existed. The journey of understanding black holes is not a path toward a final destination, but an endless exploration of an infinitely rich and complex reality. This eternal quest also reflects something profound about the human spirit. We are creatures driven by curiosity, compelled to ask questions about the nature of existence, motivated by a deep need to understand our place in the universe. Black holes represent the ultimate expression of this drive. They are the most extreme, most mysterious, most challenging objects in the cosmos, and yet we cannot resist the urge to understand them. The quest to understand black holes is also a quest to understand ourselves. In pushing the boundaries of knowledge, we discover not just new facts about the universe, but new capabilities within ourselves. We develop new forms of mathematical reasoning, new ways of thinking about space and time, new approaches to the deepest questions about reality. The study of black holes doesn't just change our understanding of the universe, it changes us. Future generations will look back on our current understanding of black holes as primitive and incomplete. Just as we look back on the physics of a century ago, they will have tools and concepts that we can barely imagine, insights that will make our current theories seem quaint and limited. But they will also face new mysteries, new paradoxes, new challenges that will humble their understanding just as black holes humble ours. The eternal quest to understand black holes reminds us that science is not a collection of facts, but a way of being in the world. It's an attitude of openness to mystery, a willingness to be surprised by reality, a commitment to following the evidence wherever it leads. In studying black holes, we participate in the grand human adventure of trying to understand the cosmos, an adventure that began with our earliest ancestors looking up at the stars and wondering what they were. And so, we reach the end of our journey through the strange and wonderful world of black holes. We've explored the places where our physics breaks down, where our certainties crumble, where the universe reveals its deepest mysteries. We've seen how these cosmic monsters humble our understanding while inspiring our wonder. Perhaps you're now looking up at the night sky differently. Perhaps you're wondering about the invisible giants lurking between the stars. Perhaps you're feeling that delicious vertigo that comes from realizing how much we don't know. Are you currently experiencing any unusual side effects? A sudden urge to contemplate infinity, an inexplicable fondness for curved space-time? Don't worry, This is perfectly normal after exposure to black hole physics. Have you ever wondered what it would be like to fall into a black hole? If you found comfort in this cosmic journey, please consider giving it a like or subscribing. It helps me continue creating these peaceful explorations of the universe's greatest mysteries. Sweet dreams, fellow traveler. May your sleep be filled with gently curved spacetime and the soft whisper of cosmic mysteries waiting to be discovered.